So we're here with James from the at Inductica channel, and he's been working with Chantel Roth on doing simulations to simulate the ether, to simulate a medium for the propagation of light. And it's the ether that we're talking about is more than just a medium for the propagation of light. It also is the reason we have magnetic fields and electric fields. At least that's my opinion. So it's more than, it's not just the traditional, only the medium for the propagation of light. This is like the foundation for everything that exists in the universe, in matter and everything, in my opinion. So
you would be
this is what
responsible for the,
Yeah.
the waves that are associated with, protons, neutrons, and electrons,
Yeah,
be associated with gravitational waves, everything.
exactly.
That's the hypothesis.
Yeah, and I think there needs to be a foundation for the universe. I think the universe isn't empty, it's full. And so, in order to prove this, we have to do a lot of work. And so I'm just presenting today just a little piece of the puzzle that might help us get to understanding physics in terms of an ether foundation. And so that's the motivation for my work. I just wrote something here. I'll leave it to the audience to read it. But basically, my motivation for the work is to see if there is an ether, or if I can prove that there's an ether, or that we can intuit an ether from the equations that we already have. So we don't need any new equations. Everything is fine in terms of physics. The problem is with the language. And this is something, James, I always say on my channel, the problem is with the language, how we say things and how we interpret the equations, okay? And so what I did was I developed something which I refer to as modified unit analysis. And so what I did was I modified unit analysis to include the cycle term as in cycles per second, and a radian term. So we kind of need both. You can't just have cycles or just have radians. Cycles is about how many cycles is in a frequency, and radian gives you the ability to express a phase. Okay, so I think that, you could use degrees as well. We could actually.
And the difference here is that in normally these units, cycles or radians, are actually unitless. That's the traditional way of doing it. And you're proposing this fundamental change, which has far-reaching implications. When you change one thing, it doesn't just change one thing. It changes a lot of things.
It really does.
But maybe for the better. So we'll see.
And that's what I hope. Yeah. I wouldn't be doing this if I didn't think that it was, going to lead to something better.
Yeah.
But, I'm not going to, make any assumptions. Let's just go through it and see if it makes sense. And so one thing I want to point out is that normally they refer to unit analysis as dimension analysis. I don't really like that term because the word dimension has a very specific meaning to me. As a computer scientist, I think of dimension as dimensions of space. So X, Y, Z, coordinates, that sort of thing, right? So, so I don't see second as a dimension. I like to call it maybe a domain. It's a domain, so it's the domain of time. So the second is the unit of the domain of time. The meter is the unit of the domain of space. So they're not dimensions. And so the reason they, I think, made cycle and radian dimensionless, or, like unitless, is because they don't really have a dimension. So it is kind of dimensionless, but it's not unitless. So to me, unit is a symbol to put into the unit analysis in order to see what's in the equation, right? In order to better interpret the equation. And so when you leave stuff out, you're hiding something, right? When you leave stuff out, you're hiding. So that's why I refer to this, I very specifically refer to this as a unit analysis and not dimensional analysis, because that's where I get into trouble.
My dimension of unit is the same as Ayn Rand's. My conceptualization of what unit is. And I have a feeling this conceptualization might be even more consistent with the way you come at this. My conceptualization is a unit is a thing out in reality considered as a member of some group. So when we say that something is a meter, we're saying it's one thing that's a member of the group of things that are 1 meter. When we say something's 5 meters, we're saying, well, it's like that, but 5 of it.
Yeah.
And
Yeah.
under this same logic, it would make sense. Like, well, we don't want to call radians or cycles unitless, because those are units. Cycles are units. Cycles are, instances of a thing, of a certain group of things.
And you can count them, especially cycles. You can count them. And that's actually the reason they said they were dimensionless, is because they're just countable. And so that's, that's why they did it the way they did. And it's not like, the second where you can, measure it. It's not but you can measure a radian. And so I didn't
and when you count muffins, like the unit is muffins.
Exactly.
Like, that's fine. That's fine. Like, that's the unit. The unit is muffins. That's what you're counting.
Yeah. And then when we're done with this conversation, I'm going to go make muffins, because now you got me thinking about muffins. Okay. So let's just continue here. So like in standard unit analysis, historically, the radians and cycles were treated as dimensionless or unitless in order to simplify the equation. So that's why they did it. In other words, it's done for mathematical convenience. But often in physics, mathematical convenience leads to conceptual ambiguity and loss of information. And that's what I feel like we lost some information here. So the radians and cycles were removed, not because they're meaningless, they're obviously meaningful, but because mathematics demanded simplicity, and the standard bodies, by convention, the people that made these decisions, chose convenience over clarity. Okay, so that's my opinion. In modified unit analysis, I reintroduced radians and cycles back into the lexicon of the language of unit analysis in an effort to remove the ambiguity and improve clarity and, maybe fix a broken language. So the language, I feel like, is broken. And so it's interesting that when I first started digging into this, this was on the Wikipedia page for Planck's constant. Okay, so in here, in this paragraph here, they talk about radians and cycles and how Planck's constant has units of joule times second per cycle, and reduced Planck's constant has units joule times second per radian. So this was on the Wikipedia page, and then so I made a video about it like years and years ago, and then I went back to look for it, and it was gone. It was gone. It's not there anymore. So I went to the Wayback Machine, and it was there. And so I wasn't hallucinating. It was definitely there. And obviously I cut and pasted this from the Wikipedia page. And so I tracked down the person that wrote the paragraph, actually. That somebody else took it down, but somebody that wrote it. And then, so they had sort of some theory that they were working on, and they had put this in and someone took it out. So that's kind of interesting that it got taken out. This is like so important, and yet someone didn't think it was important enough to leave it on the Wikipedia page for Planck's constant. So I found that kind of interesting. So I want to put it back in, but I don't know how to do that. You have to you can't just change a Wikipedia page. You have to have someone give you permission to even edit anything on a Wikipedia page, and I don't even know anyone that could do that for me. So anyways, that was kind of interesting. So, Planck's energy equation is one of those mathematical formula that suffered greatly, I believe, from the removal of radian and cycle from the language of unit analysis. So not dimensional analysis, I'm calling it unit analysis. So as you will see, restoring these units to their rightful place leads to a completely different interpretation of Planck's energy equation and potentially the nature of light itself. So the question is, so the purpose is to answer these questions. So is light made of photons? Do photons exist as specified? Because obviously light exists, but is it really photons? And the other question, of course, is there a medium for the propagation of light? So is light a photon, and is there a medium? And, so what, can both of these tell us about the nature of light? Because we just want to understand the nature of light. But with the ether, it also maybe tells us about the nature of matter and the nature of matter's interaction with light, right? So these are all the things that we need to talk about. Okay, so Planck's energy equation, there are two versions, of course, of Planck's energy equation. There's the one with H and there's the one with H bar. When you use H, you have to use frequency, and when you use H bar, you have to use omega, angular frequency. Okay, but interestingly, the units for frequency and angular frequency in, the standard language is exactly the same. Okay, so they report like hertz in as 1/2. And this one here is the problem. This is what bothered me. This is what kept me awake at night. Like, this is the numerical value. They put the numerical value of 1 into the unit section, and then they use it as the numerical value of 1. So, these units work out to joule only if you use 1 as the numerical value of 1. And I think that's a mistake. Okay. And also they use the same numerical value of 1 for angular frequency. So when you look at these units, you can't tell the difference between, which equation you're using when you look at these intermediate units. And so when I do unit analysis, I like to write the units down in full. It's kind of like showing your work when you do a mathematical, equation in high school. You have to show all your work. I'm sure trying to show all the work. So here, H has units of action, joule times second, but H bar also has units of action. Okay, but they're different numerically. So these things kind of bother me. Why, what's different about them?
So something that bothers me immediately here is 1, you can ask 1 what?
Yeah.
Now, the answer, now, I think it is appropriate to just talk about 1 because 1 + 1 is 2. 1 + 2 is 3. Like, those are true statements. But when you say 1 + 1 is 1, you're not ignoring the unit. You're omitting the unit. There has to be 1 and 1 of something. Exactly. Now, you don't need to specify it, but you don't need to specify it, but you need to be able to specify it when called upon, because at the end of the day, there is no such thing as 1 apart from 1 muffin or 1 joule or whatever it is.
Yeah, that's a good point. Yeah. Yeah. Excellent point.
And that's what would be 1 here? This is the reason, maybe the reason it's bothering you is this is a context where you have to specify what the unit is. Like, because it's literally the unit that these brackets mean. This is the unit slot. This is where we talk about the units. Exactly. You can just have 1. 1 isn't a unit. Yeah, that's cool.
And also I could put 1, I could alternatively put 1s in all of these positions too, because joule is 1 joule. Second is 1 second. It means 1 second. Like, technically it means 1 second. Right? It means, that's why it's called a unit. Unit is 1. And so the logic here, I think, was kind of poor. But so what I want, so what I did here is that, okay, let's pretend 1 is a symbol. It's not the numerical value of 1. Now these units aren't balanced, right? Because something has to cancel that unit. And so, right? So then I do this. Right? So then I do this. So this cancels that cancels that, and it's nicely balanced. I'm a Libra, and I like balance. I like things to be balanced, and so that's probably why this bothered me so much, because it wasn't balanced. But now it's balanced. Okay, but I don't want to put the numerical value of 1 because I think that confuses people. Okay, so I want to distinguish the units, and the way I do that is, I went too far here. Okay, is I put symbols in. Okay, so for this equation here, for the one with the H, you have to, these are cycle terms. So instead of 1, you have cycle. And for the H bar omega 1, the 1 turns into a radian, So now we know 1 watt. In this equation, it's 1 cycle. And so the units of action become action per cycle. So whatever action is, which is, kind of a weird unit. I'm getting actually a little bit of a better understanding of what action is from that email that we got from Chantel. So I did sort of a deep dive. I actually got her to give me that conversation, and I had I continued the conversation with ChatGPT on this. And it's the same as what I'm saying, which it turns out, which is kind of ironic. But so now we've got everything nicely balanced, and we've got the radian term, and the delta terms in here. Okay, so what I want to do is I want to walk through the process of how I did this. Okay, I just plugged them in right now, but I want to explain why I was able to do this. And so, what I did was I expanded the energy equation to expose the 2 pi term, because, there is a 2 pi term in here, and 2 pi in modified unit analysis has units itself. It's not unitless. It's only unitless when you hide the radian and the cycle term, but when I expose the radian and cycle term, then I have to say that 2 pi, it has units radian per cycle. And so that's how I inject the radians and the cycle back into, that's how I justify putting them back into the units. And so, 2 pi is the number of radians in one cycle, right? It's literally that. And so this is basically how I justified doing that. Okay. So now we can plug in, we can go the old way and use the, put the one here and put the one here, right? And then when I put radians per cycle into the formula, into the units, then, I have to rebalance the equation. So this formula, this units are not balanced again, because this cancels this cancels this, and now I have joules times radian per cycle, which is not, this isn't correct. This is not correct. So what I had to do was, in order to balance it, right, so I had to put the radian here and the cycle here, and now everything's balanced. And so now you can, right, so now you can see, we already knew from before that the units of H bar is joules times second per radian, right? The units of 2 pi are obviously radians per cycle, and the units of cyclic frequency is cycles per second. So now everything balances, and we have like a beautiful way of looking at this equation. And so, yeah.
Now I have a quick question. So to me, when I ask myself, okay, well, what's a radian? I'm very clear on what well, first I'll just say I'm clear on what a cycle is. I'll tell you what my view of what a cycle is. It means one repetition of any repetitive process, repetitive process. So a couple of examples, so like obviously the oscillation of like a block, that's a classic physics example. And then to give an example, people may not think about it that often, is like I airsoft, and like the cycling of my airsoft gun, it pulls a spring back and then launches it forward. So that's that whole process of back and then forward. That's one cycle. And the unit, and that can be a unit, because the idea is well, it's any instance of a repetitive cycle. Radian is totally, a little
So radian is,
what do you see radian to be? I have a view on this, but let's hear yours first.
Okay, so a radian in geometry is defined as the angle such that the arc length of the circle is r, is the radius, equals the radius. Right? So I should have put a slide. I don't think I have a slide for that. I show a slide for that. But so you can imagine there's a circle and there's a pi cut out of the circle, and that angle is 1 radian, and the arc length of that makes on the circle is equal to the radius. So that's how it's defined. Now, the reason we need radian is so that we can define an angle. So if you want to make angular measurements, then you need to have the radian. So the radian is, how we do. So it doesn't have to be on a circle. So a radian can be generalized to the phase of the cycle. So at what phase are you in the cycle? And so that's why you need radian. Alternatively, like here, I could use degrees, because I like degrees. I do build medical devices, and we run motors, and I don't do anything in radians. I do everything in either RPM, rotations per minute does not mean radians per minute, it means rotations per minute. So when I'm dealing with motors or encoders, then I need to know how many times the motor turned, or in the encoders, I need to know the phase angle of the encoder. So we build these mechanical arms, they're mechatronic arms actually, that we move around, and each joint has an encoder, and I need to know what angle it is in order to do the kinematics. And so I use degrees. I don't use radians. It's not practical as an engineer, as even a computer science to use radians. So I always use degrees. And then just before I do the cosine, I switch to radians. Okay, so radian is the natural unit of sine and cosine. So sine and cosine naturally takes radian as a parameter, and that's because of the Taylor series, right? So I did have a slide on the Taylor series, but I don't want to get into that. We can,
basically, in order to calculate sine and cosine computationally using a Taylor series, you got to put in radians. You can't put in degrees. Otherwise, you got to you got to make the Taylor series. You got to screw with the Taylor series in a way.
Then you have to put 2 pi in every term. So it makes it really.
Oh yeah. Oh okay. Yeah. You don't want to do that.
Converting, and then did it in cycles, I'd have to multiply each one by 2 pi. So I tried that, and you can't I can do it if I want to, but really what I want to do is convert to radians. So I do degrees, I convert to radians, and then I do the sine and cosine.
Yeah.
And that's the most. Yeah. It's not as efficient as always working in radians, but radians don't make sense to me when I'm doing kinematics. I need degrees. Yeah. I know degrees. Yeah. There's an exact number of degrees in one cycle. There's 360 degrees in one cycle, but there's not an exact number of radians. There's an irrational number of radians in one cycle. So it's not practical to use. It's just, and that's where the mathematical convenience. So they chose mathematical convenience over clarity, right? Over, So a lot of physics, and that's why they use H bar. They always use H bar so here's the cool thing. When you're calibrated, so when you're using H bar.
Before we move on, I just wanted to give my view of what a radian is, which is,
sorry.
It's pretty much the same as yours. I just want to emphasize something, which is that we tend to think of a radian as an angle. Radians is some measure of angle, and that's fine. You can think of it that way. But in this context, we're broadening it. It's a certain fraction of a cycle where 6.28 blah, 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 blah. Radians is one cycle. Now, why did we do that? Because we're using the cycle of geometric circularness. There's probably a better way to say that, but we're using one cycle in nature of going around geometric circleness. And we're using that as an analogy for the phase of any cycle.
Exactly.
And so in this case, radians are broadened away from angle and towards just some fraction of a full cycle.
Exactly. And degrees is also a fraction of a full cycle. So I could literally switch this to degrees. And if I did that, then I would have to invent a new H, which I did in one of my videos. I called it H with a dot on top or something like that. Mm-hmm. And everything would work out fine. Yeah. We could do degrees if we wanted to. We just have to change this parameter here, right? So we don't have to use radians. It's just, we do. And I don't want to make another H. Like if we want to use degrees, we could. But, in physics, they don't really need degrees. So they really need radians if they want to use cosine, sine, and cosine. So I understand why they want to, use radians. Then they don't have to put 2 pi, they get rid of a lot of the 2 pi parameters in their equations. But actually, sometimes it's better to work in cycles. Like in the Fourier transform, is actually better to work in cycles. And then they have to convert to radians to do the sine and cosine. So, it's really a matter of what are you doing, right? As an engineer, I like cycles, I like degrees. And so engineers...
And it's important to note that today what we are primarily concerned with is not necessarily computational ease, as important as that might be. Yeah. We're interested in units which reveal aspects of the hidden physical nature of what we're talking about when we talk about this E equals HF.
Yeah.
What are we talking about? Can we change the units in such a way to reveal what we're talking about?
Yeah. Exactly. And that's the whole point of this exercise. Okay, so so now we can group the units, either the 2 pi. So this 2 pi now, we kind of want to make it disappear because then we know it has units now. We know what the units are and we know how it maps out. So if you want to use H, right, then you group the 2 pi with the H bar. Or sorry, if you want to use frequency, you have to use H. And if you want to use H, you have to group the 2 pi with the H bar. And then you can do the, unit analysis here. So, H bar is units, joules times second per radian, angular frequency, joules times second per radian, 2 pi as units radians per cycle, and frequency as units cycles per second. And then you end up with these units here. Okay, so when you want to use H, when you're calibrated, so if you want to use H, then you're calibrated to the cycle. That's how I like to say it. So this energy equation, this equation here is calibrated. I like the word calibration. I do a lot of calibration in my lab. And so you're calibrated literally to the cycle when you use H. And that's an important detail that you miss when you don't do unit analysis this way. You really miss the fact that you're calibrated to the cycle. And so, but if you want to use H bar, then you have to group the 2 pi with the frequency term where then you get angular frequency. And when you do the unit analysis, you end up with, so instead of cycle terms here, you have radians here. And so this is, these are the units when you're calibrated to the radian. So whenever you use H bar, you have to use angular frequency. And when you use angular frequency, you're calibrated to the radian. Okay. So, they're both useful and they're both used in physics. When you look through physics, sometimes you see H and sometimes you see H bar. And so now you can look at those equations and say, okay, so when I see H, we know we're calibrated to the cycle. So that's one intuition that you maybe didn't, I certainly didn't have before I did all this. I'd see a paper where sometimes they use H and sometimes they use H bar, and it's, then they have to do a conversion, and then they have 2 pi's and then they don't have 2 pi's, and it gets really ugly. And so this really kind of brings a lot of clarity to, I think, when to use H and when to use H bar.
Yeah.
Okay. So now we have, these two very clear, right? So we can clearly distinguish between the two versions of Planck energy equation just by looking at the intermediate units. Okay. So, what does this buy us, I guess, is the question. And my answer to that is just interpretation, right? It doesn't change the physics. The physics is still the same, but it does give us more opportunity to interpret things differently, maybe more clearly, maybe, gives us more opportunities, I think, to mess around with these units and see kind of how far we can take it.
Well,
right?
let me offer a small objection here. I would say it does change the physics. It doesn't change the calculation.
That's what I meant.
Okay. Yeah,
Sorry,
because you're now asserting there's a cycle here. Something's actually doing a repetitive process. And that's in line with our physics as opposed to mainstream physics. And part of what, I don't know if you necessarily fully agree with me on this, but I mean, I think there's an ether. There's a physical object. Maybe you agree with this part. You don't necessarily say there's an ether, but you agree that there's a physical object or set of objects doing a repetitive physical process. It isn't just math. You agree with that much with me.
So there must be a medium is probably the strongest statement I can make. There must be a medium, a foundation, a medium, whatever you want to call it. And of course, I believe it's true. I just, I haven't proved it yet. So I can't say I proved it. That's the only thing I can't say. I'm working towards it. I'm trying to see if I can see it. If I can see it, then I can get other people to see it.
This is a bit of a sidetrack, but are you aware of what I believe I've proven it in several different arguments? Are you aware of my arguments?
Yes,
have we talked about that?
Yes, I have.
Okay.
So I understand.
That's a question. That's a conversation for a different day.
I don't disagree with anything you said. There's nothing you said that I could say, oh, that's wrong. right? So I agree with your logic, but scientists want to prove things mathematically, right?
Yeah, well, they're wrong.
So yeah.
But they're wrong to do that. Like there
Yeah.
are ways to prove things that don't use math. Also, incidentally, I did use math. Like like one of my proofs uses math.
Yeah, okay. I
So
I have to look at
uh
that more closely
yeah,
then.
yeah.
Yeah.
So but also it's worth noting that like it, you know, you know, proof is not a popularity contest. Proof,
Yeah.
it's like proof is
Yeah.
some method that you use that at the end of that method, you have something true.
Yeah.
That
Yeah.
you can't be wrong, or that like
Yeah.
the probability of you being wrong is so small that it isn't worth
Yeah.
considering. But
Yeah.
anyway,
Yeah, exactly. And that's what I'm like doing here is I'm like I'm not wrong. There's nothing I did here that's wrong, right? And it does lead to a different interpretation. It's whether that interpretation is right or not. You know what I mean? And both interpretations could be right in a sense, right? So you can have two perspectives. You can say it differently and it might sound different, but it means the same thing. Okay, so there's a famous quote by Richard Feynman that I almost always quote when I write a paper. There's always another way to say the same thing that doesn't look at all like the way they said it before. That was Richard Feynman. When he gave his Nobel laureate lecture, he said that in the lecture. And so I felt like that was a really profound statement. That's a statement that kind of drives me because I'm just trying to say it differently to get right. And so
what do you take to be the alternative true way of saying it? So one way is that there's an ether or medium. What's another way that's just as right?
the way they do it now, and they're
You
very
think that's just
successful.
as right?
No, it's just not wrong. Like it's not wrong.
Okay, I mean,
Like
but
not like using the word right,
think
right? It's just
I
which one
think
is better. And I think the simpler solution is better. And I think it's actually simpler and I have arguments with people like this all the time, like every day, practically. Right. It's, I think it's easier. So then you're down to this like Occam's razor. So I think it's easier to have an ether. And other people say it's easier to not have an ether, that the math works out and you don't need to have an ether. So I actually think it's easier to have an ether. So that's the argument. It's like, I think it simplifies the concepts. Like we know what a wave is in a medium, right? So to have a wave that doesn't have a medium is illogical, even though they can do the math and pretend there's not a medium. They can ignore the medium, which is what they're doing really. They're just saying, oh, we can ignore the medium because of relativity and all that stuff, like they can ignore it. That's really what they're doing. They're just ignoring the medium. It doesn't buy them anything according to their logic. And so, but I think it does buy us something. It buys us a better intuition.
I
And
see.
so,
Yeah. I have a different view on this. I think ease is a completely secondary consideration. I think the question is, what are the facts? And the facts are that you can't have a property without an entity that bears that property. You can't have properties just floating out freely. And so as a result, it's not just a matter of ease. It is a fact that there's a medium. And mainstream physicists are not just, they don't just have this alternate view. They're wrong when they deny that medium. And they don't just ignore it. They deny it.
Yeah,
now,
they do.
if
They
you
do.
want
They
to remain
deny it.
silent about the medium, if you want to actually ignore it, then yeah, you're not wrong. Because you're abstaining on a certain issue, and it might be fine to abstain from that issue. You might just say, hey, look, I'm just gonna look, this is great, Lori, like that you're talking about this. Maybe you'll figure something out. But I'm an engineer. I'm just gonna talk about fields. That's fine, because the fields really do exist, and they really are properties of this medium. And if you just don't want to be a physicist, well, that's fine. You just want to talk about the fields, then you can focus on that. But mainstream physics goes beyond that. They deny the
They
meaning.
literally deny.
It's
Yeah.
their fault. They are uttering falsehoods.
Yeah.
It's not just
Yeah.
a different perspective.
That's true. They literally deny. I know I work with physicists, and, when I bring up the concept of the ether, they mock me.
Yeah, and I mean that's rude,
Right?
but like any
Yeah.
rudeness aside, I mean they're just wrong. And with that attitude, it hinders the further development of physics. So,
Sure. Yeah,
yeah.
it's like, why not pursue this line of thinking and see where it goes? It's not a waste of time. Even if we're wrong, but I don't think we're wrong, it's not a waste of time. If it buys us a better interpretation, if it, and so the main thing that I get, the question I get, or the statement I get is, doesn't make any predictions different than what we predict right now. Well, what if it doesn't? What if it predicts everything exactly the same, perfectly, makes the same predictions 100%, isn't that good enough?
This is equivalent, by the way. This kind of thing is equivalent to the mindset where someone says, well, why does it matter if I'm lying if it gets me what I want and no one finds out that I'm lying?
Yes.
Well, the reason is it's not going to work out. Reality isn't just this tiny box that you live in right now where you got away with it in that tiny box, and then and no, now you have to continue that lie for the rest of your life in order. So if that subject ever comes up again, where did you get this money? You're going to have to lie again, and then you're going to lie again and again and again. So it's like, if you only look at the stuff that's directly in front of your face, you can justify any behavior, really. And so there's like, oh, well, this doesn't generate any predictions in the near term. In other words, they're just like, well, why does the truth matter if it doesn't buy us any advantage in the near term? And similarly with the liar, why does the truth matter if I can get free goodies, defraud someone and get away with it in the near term? Well, you're not thinking about the long term and how, this lie can ruin your life. Just watch Better Call Saul, and you will see how bad this pragmatic philosophy is.
Yeah. And, that's what, the way the physics went with, first denying the ether, and then each thing that they built on top of that was maybe one lie upon one lie upon one lie, just like you're saying. Like and it works out, the math works out, but that doesn't mean you're getting the right interpretation. And, and like you say, maybe they don't care. Maybe they don't care. It gets the right answer. They can build their machine. The machine works perfectly based on their math, and they're happy, right? Or they do an experiment, and the experiment, the results of their experiment is what they predicted with their math, and they're happy, right? And so I'm not happy, I'm not happy, just calculating and getting the right answer. It's not satisfying to me.
That mindset is fine if you're an engineer, but so long as you have it, you are nothing but an engineer. You are not a physicist or maybe you're some kind of very narrowly applied physicist, but you are not a true theoretical physicist trying to identify the nature of the physical world.
Yeah, exactly. So I'm going to do something a little different here that I just sort of came up with this in the last couple of days. Cool. Just another way of using modified unit analysis. And this is a very important part of the puzzle in terms of understanding the ether. So we didn't do this. So, you and I talked about this before, and we didn't record it, which was my fault. But it was good that we had that conversation, because now you're a little more up to speed in what I'm talking about. So we're not kind of struggling as much as we were last time. And so I wanted to do this as kind of interesting regarding the fine structure constant. Okay, so when I apply modified unit analysis to the fine structure constant, I find that the fine structure constant has a unit. It's not unitless.
Radians.
Yes. Okay, so here's how you calculate the fine structure. This is one way. There's many ways, but this is one way. Okay, so this formula you'll find right at the beginning when you look up fine structure constant. And so I mapped out the units. And so of course, this one here is the Coulomb constant. So just to package it a little nicely. So it's the Coulomb constant times elementary charge squared times reduced Planck's constant times the speed of light. So when you map out, so the Coulomb constant has these units here. Okay, and of course, elementary charge is the Coulomb squared. And then you've got the h bar is joule times second per radian. And speed of light, of course, is meters per second. And so I'm going to take all the junk here from the bottom here and move it up to the numerator, from the denominator to the numerator. So these reverse. So it's just easier to cancel when you do that, right? So when you take this junk down here and put in reverse them and put them over here, then this cancels that, this cancels that. Oh yeah, and I took one of the meters out of here and put it into the Newton, so we get the joule, right? It's just, you know, I'm just doing algebra now, basically, on the units. And so you've got, so instead of Newton meters squared, Coulomb squared, you've got joule meters per Coulomb. It's just, I'm just reorganizing the units so I can cancel them better. This cancels that, this cancels that, that cancels that, the joule cancels that, and you end up with the units of radian. So, you know, I did a kind of a deep dive into last couple of days into the fine structure constant, just to see, like, you know, I did a lot of, like, over the years, I always go back to the fine structure constant because it's so mysterious, right? Even Richard Feynman thought it was mysterious. And so because it's unitless. So because it's unitless, or at least assumed to be unitless, it survives unit changes. So if you, like, when we switched from the CGS system, the centimeter, right, the CGS system to the
same
MKS
number,
system, right, all the other constants had to be recalibrated, right? So in the CGS system, the gravitational constant is not the same number as in the MKS system. And same with the Coulomb constant, same with all the constants, same with even, you know, Planck's constant, right? And the speed of light is different because you're measuring, you know, centimeters instead of meters. So all the numerology has to change except for the fine structure constant. The fine structure constant is still 0.007, blah, 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 no matter what system we choose. So when we go to the natural units, right, you know about the natural units where they use Planck natural unit, right? When, you know, so then, you know, again, you have to change. Then the gravitational constant is 1. You know, it makes all the constants evaluate to 1, even though they still have units. And the fine structure constant is still 0.007, blah, 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 blah. Okay, so that's why it's so mysterious to everyone, because it survives these unit transformations, I guess you can call them. So that's, you know, it's unitless. It's only unitless if you don't put radians and cycles into the unit analysis. When you do, then it has the units of radian. Now, interestingly, radian also survives unit transformations. So in CGS, a radian is a radian. In MKS, a radian is a radian. In natural units, a radian is a radian. So it has this same property in that it survives the unit transformations, right? So, but it has units of radian, which tells us something. So instead of just saying it's unitless, if you just say it's unitless, it's mysterious. It's, what is it? But if you say it has units of radian, that means something. I don't know what it means yet. I'm digging deep into this because it obviously means something. And so all these constants of nature, so fine structure constant, Planck's constant, the speed of light, permittivity, these are all properties of the ether, right? So alpha is also, so if you switch, say you switch H and alpha, so then H bar is equal to, you know, Coulomb constant times E squared over alpha time, you know, divided by C. So, you know, like you can see that all the junk in here, permittivity, has to do with the medium, right? It has to do with the ether, in my opinion.
Mm-hmm, mm-hmm.
Right? So this is telling us everything we need to know about the ether. Okay, so now I'm going to do something. Okay, go ahead.
I have some questions about this. So
Okay.
first, can you remind me and our audience give us just sort of the most basic review of the fine structure constant and where it arises in physics?
Right.
Because I'm forgetting just even the undergrad understanding of what it is.
It is. They refer to it as a coupling constant, and it's sort of between. It's hard to explain.
Yeah,
like, I
would
don't
imagine
know.
so.
I don't even know
You can't even give me an undergrad version because undergrads don't know what the hell they're even studying. They memorize this.
It's very confusing. But to me, it seems like it's now my deep dive with ChatGPT on this, like it's a lot of things. It's not just one thing. It shows up in quantum electrodynamics. It shows up in everywhere. And so I'm going to tell you what I think alpha is. It is like a gear ratio. It is like a gear ratio. So it couples the strong and the weak, or it couples electromagnetism with just off the top of my head, I'd have to map that out and maybe do another presentation on the fine structure constant. It kind of shows up everywhere, but in each circumstance that I looked at, it seems like it goes from a weak to it's a conversion factor from a weak condition to a strong condition, which makes me think of, like, as a engineer, it made me think of a gear ratio. It's like a gear ratio.
That's very interesting, because that leads me to my next question. Like, I don't even know what your evidence is that it's a gear ratio, but that somehow sounds right, because here's my next question.
Yeah.
You see how there's a 4 pi on the bottom?
Yeah.
Doesn't pi have units of radians? And didn't you forget about those units?
Oh, no. Okay, so this is, I know, yeah, I had a feeling that was going to come up. That's why
here's why the gear ratio thing made sense to me, because then wouldn't that lead to units of radians over radians, which I recognize is unitless, but radians, it's equivalent to radians over radians. And isn't that a gear ratio? Because it's the number of radians that one gear turns in proportion to the...
Yeah.
Okay, that's where I was going with that.
Yeah.
Okay, why did you not miss the radians on the bottom?
No, because because of the Coulomb constant. So I think that they pulled out, they took the Coulomb constant and they pulled out the 4 pi kind of geometrically. So it's not dynamic. So 2 pi is more of it's kind of a dynamic, like we're talking about.
This is a spatial pi.
It's a spatial pi.
Cyclical pi.
Yeah, not a temporal cyclical pi.
Because the reason this pi is there.
Yeah.
Well, I mean, I'd actually have to think about it. Like, if this really is Coulomb's constant, I'd have to look at a derivation of the fine structure constant to see what kinds of physical considerations go in. But if those physical considerations are identical to those of the Coulomb constant, and really the Coulomb constant is supposed to be sitting there, then that 4 pi refers to the surface area of a sphere.
Exactly.
Because it's the Coulomb spreading of the influence over a sphere.
Yeah. So that's a very important, you'll always see the 4 pi right beside an r squared, right? So when you do, right? And so when you look at the, where permittivity is used, there's always like the 4 pi. So it's used in, so this is the Coulomb constant. So the Coulomb like in the force equation, Coulomb constant times, the charge squared over charge squared over the space, charge squared over the spatially r squared. So it's F equals Coulomb constant times, charge squared over radius squared. This 4 pi goes with the radius squared, 4 pi r squared, of course, is the surface area of, so that's why I put the 1 over 4 pi permittivity as the Coulomb constant, which it is.
Yeah.
Just to bury that 4 pi back into the Coulomb constant where it belongs, right? It doesn't have units like the 2 pi. Because 2 pi is literally, right?
Yeah.
4 pi
You've
is...
definitely yeah, sorry.
Yeah. So that's why, like, I kind of wish I just put the Coulomb constant, because I don't want to, like, I knew that was going to come up.
Yeah, you've satisfied, you've definitely...
Yeah,
sorry, we keep running over each other. You've satisfied me for now.
Okay.
But now I have a deeper question, which is the following. To me, this opens up a can of worms with regard to pi, because we talked about how this is a spatial pi, not a cyclical pi. It can't be treated as a cyclical pi generally. It must be treated as a spatial pi. It must be treated as a pi relating to the surface area of a sphere.
Yeah.
It is my strong belief. I don't know this for sure, but it's my strong belief that pi is a physical constant. Or in certain contexts, pi is a physical constant. Why? Because it's a ratio that applies to certain geometric figures. And in my view, geometry is not a branch of math. It's a branch of physics. Because geometry describes facts about shapes, and shapes are physical. So we're talking about physical properties here. Now, it turns out that we use those physical properties to aid our mathematical calculations all the time, but that doesn't change the fact that there's a basic physical reality behind the things we're talking about in geometry. Mm-hmm. And this 4 pi r squared that's implicit here is one of them. And so I wonder if you were to dig even deeper, you'd find a modified unit analysis for these spatial instances of pi. Just a thought. I'm not making any claims there. It's just something.
See, modified unit analysis to me only applies to 2 pi, not just pi. So it's 2 pi, right? 2 pi is radians per cycle, not 1 pi, right? You know what I mean? So, and also
there is a 2 pi here. It's just 2 pi times 2.
I know, but I know. No, that's good. Very good question. Like, I totally understand. I laid awake at night worrying about this. I do. Okay. And I did.
You've gone down this road is what you're telling me.
Yeah. And so it's my opinion that they pulled out this 4 pi kind of arbitrarily. Not like, right? So every time you see permittivity, you almost always see the 4 pi. So you might as well write the Coulomb constant. And then you don't have the confusion of this 4 pi compared to the 2 pi that I'm saying has units radians per cycle, right? So when you pack that back to the Coulomb constant, which we use, like the Coulomb constant is known, like we use it. Usually they put the Coulomb constant in the force equation and sometimes they put this. And so I feel like this 4 pi is sort of arbitrarily, they pulled it out so that you could see that we're talking about the geometry of a sphere here, the surface area of a sphere, so that you can see it. But it's different than the 2 pi that I'm talking about, that is about the cyclic nature of a traveling wave. Right?
I have one other proposal for you, and this may be wrong in light of what you just said, but I just want to bring it to your attention also. Couldn't you cancel this here pi or cancel 2 pi here, and then your h bar turns into an h, and now you can write the whole dang thing calibrated to cycles instead of radians, and you have cycles at the
we need to keep this because this is the Coulomb constant, so I don't want to break this up. This is the Coulomb constant. But
I don't know why we need the Coulomb constant there. I would like to see why the Coulomb constant needs to be there in terms of prior derivation, but I'm not going to bother you about it now.
No, this is just from Wikipedia. This is what, like, I actually derived this. It's going to be a longer story though. I actually derived this using using the law of capacitance. So I'll send you, I think I mentioned this in one of the emails. I'll send you, like I'm reworking it right now, but I did derive this using the law of capacitance. So I was trying to derive Planck's constant from the law of capacitance. And this is an idea I got from someone else. So someone else did it and I thought, oh, that's interesting, but I wanted to do it a little differently. And so I derived Planck's constant from the law of capacitance. And in order to do that, I needed to put that guy in there. And then this all came out. So I'll send you that and we can maybe talk about that another time. But, you know, so that's a longer story.
Yeah.
I don't really want to burden what we're talking about right now, but I do want to do what you just said. Okay, so I want to replace H. So what happens when we replace H bar with H? Okay, I can do it. I can just say, okay, I'm going to put H in there. So so then the units change, right? The units. So what is that? Can you guess? What is that? So if I change H bar to H, and now everywhere there's a radian, I put a cycle, right? So I put a cycle. And so what's going to happen is the output of this is going to be cycle instead of radian, just like, so now we're calibrated to the cycle because every time you have H, you're calibrated to the cycle. So what is that? Can you guess what that is?
Is it, my guess is that it's the fine structure constant, but in units of cycles instead of radians.
Yeah. Do you know what that is?
Value.
Okay, that's it.
What is that?
Okay, so this is the answer. Do you recognize that?
No.
Okay. It is the anomalous magnetic moment.
What?
It's the
how close in terms of the decimals? Oh, but we already know because that's like a definition.
All of them. Like here's the anomalous magnetic moment. This is my calculation on my computer. I always write all the decimal places, right? So it goes like, right, so to there, from here to here.
As long as it's significant, you should, but yeah.
It is, right. I just do because I can. Like when I run my program, these are all the digits I get and I just cut and paste them. Like, so you can see like I'm getting more digits than they have. And so it's well known that the anomalous magnetic moment is alpha over 2 pi. So, right. So obviously I had to put the extra 2 pi in here to get from H bar to H. Right. And so from the perspective of, say, modified unit analysis, when you use alpha, you're calibrated to the radian. And when you use the anomalous, they're not two different. These aren't two different constants. This is the same constant, but when you're calibrated to the cycle, you have to use H. And when you use H, you have to use the anomalous magnetic moment. That's how I see it. Now, mainstream science, they kind of present them as two different constants. So they measure alpha and they measure the anomalous magnetic moment, not realizing that they're just like two sides of the same coin. They're the same thing, but they present them as different things. And so this bothers me. And this is one thing I'm trying to figure out, because this is what comes out of my unit analysis. And it can't be a coincidence, right, that this is what comes out.
Okay, first, once again, can you give me the like undergrad explanation of what the anomalous magnetic moment is? Because I haven't studied this recently.
Okay, what I'm going to do, I'm just not good at explaining things. So what I'm going to do is I'm going to look it up. Okay, and then I will tell you what.
Look it up as well.
Anomalous magnetic moment. They just have a weird language that I can't remember. So it's kind of, okay. So the anomalous magnetic moment of a particle is a contribution of effects of quantum mechanics expressed by the Feynman diagrams with loops. The magnetic moment of a particle. The magnetic moment is also called the magnetic dipole moment. So this has to do with the dipole moment. So the Dirac moment corresponds to tree level see, this is all language I don't like. That can be calculated from the Dirac equation. It's usually expressed in terms of a G factor, which is weird. The Dirac equation predicts that G factor is equal to -2. So anyways, there's a bunch of stuff in here that I can't learn it
Yeah,
because
I don't understand it either. I mean, this.
I think it's wrong. But here you can see it's approximately, so here's the interesting thing that they say here. It's the one loop contribution to the anomalous magnetic moment. So this is the one loop. So this is the anomalous magnetic moment of one turn, one cycle. And so I get the right answer. Like this is one cycle. This is the anomalous magnetic moment due to the one loop contribution to the anomalous magnetic moment corresponding to the first largest quantum mechanical correction, blah, 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 blah. Like, again, I don't like the languages. And that's why my brain can't understand something that it is not correct.
Well, I mean, to me, this just means that there's a ton of context here we don't understand.
Yeah,
And
exactly.
and I certainly, I think it would be a big mistake to dismiss it, because my view of modern mainstream physics is not that stuff like this is just crap. It's that it's onto something. It's not crap. It's onto something. It's telling us something real, but we're unclear about what it's telling us. And so that as a
Exactly.
result, like when you and I like read the Wikipedia page, like even after all our years of physics, like, I don't know what the hell that is. Because
Exactly.
well, I mean, now that's not, I mean, that could just be because we haven't studied the necessary particle physics. But
Exactly.
once I do, and I intend on doing it eventually, once I do, like, there's going to be an enormous amount of context to understand there. And once again, I am skeptical that mainstream physicists really understand that context, because of course we already know that as early as quantum mechanics, forget about higher level particle physics like this, but as early as quantum mechanics, they threw out the ether, they threw out physical interpretations of what they were doing.
Yeah.
So yeah, and there's all kinds of unanswered questions that I think we need to answer here in order to get a clear picture. For example, this ratio between the fine structure constant and the anomalous magnetic moment, alpha over,
2 pi.
alpha over 2 pi equals anomalous magnetic moment. Like, is that derived from known theory, or is that a highly well-measured ratio where they just happen to measure the anomalous moment and they're like, my God, it's exactly, the same as dividing the fine structure constant by 2 pi? Is that how they got it? I kind of doubt it, because that would be...
I think it was derived, but then they came up with a way of measuring it. And when they measure it, it's a slightly different value. So this bothers me because what are they measuring? Like, I have to look into what they're actually measuring. And so the anomalous magnetic moment has a bunch of terms, I think, kind of like a Taylor series kind of a thing. And then when you do that, you end up with this sort of a different number than my exact number. So the exact number is the one, they call it the one loop contribution. And the way I kind of see it is it's the contribution of one cycle. Mm-hmm. But if you had many cycles, then maybe those cycles sort of interfere with each other and you end up with a different number. I don't know. Right. But for the one cycle, like if you had a loop of wire and it's just one cycle, then you would get a certain effect. So that's all I know. Like, this is just a sketch of how I was able to sort of derive the anomalous magnetic moment from alpha, sort of using my modified unit analysis. I was able to intuit that, just by replacing h bar with h, I was able to get the anomalous magnetic moment, at least the first iteration. Let's call it an iteration. I think that loop is kind of like an iteration. It's the first iteration of which was derived. And then when they measure it, they get a different value. And I'd have to look at the experiments to see how they're measuring this, to see, why they end up with a slightly different value than, like, slightly lower value actually than, where is it here? So it's 0.115 instead of 0.116. So I don't know why.
Yeah. So the take home message for me is whatever our feelings are worth, our feelings say that this can't be a coincidence. This has
Right.
to mean something.
Exactly.
For whatever our feelings are worth here.
Yeah.
Which they might be worth something. I mean, our feelings are worth
Yeah.
nothing on their own, but like
I think our
it,
our gut feeling is worth something. Our gut, if you have a gut feeling about
it
something,
means you should keep
it's worth
looking. It doesn't prove
exactly.
anything, but it means
Yeah.
you should keep looking to find a proof.
Yeah.
So
Yeah.
yeah.
So in terms of like, what does it mean to me, right? These two, you know, fine structure constant and anomalous magnetic moment are two sides of the same coin. They're the same thing. Only when you're calibrated to the radian, you have to use alpha. And when you're calibrated to the cycle, you have to use the anomalous magnetic moment. That's what I'm seeing. That's what I'm seeing. And so in terms of, being a calibration parameter, I think that's basically what I'm seeing here. For what it's worth, whatever it means, they're both they're the same thing. They can't be different things, in my opinion. They're just, if you're looking at cyclic, then you have to use frequency, and if you're using frequency, you have to use H, and if you use H, you have to use the anomalous magnetic moment. That it seems obvious to me. So if I'm wrong, I'd like to know why.
Right.
It
seems like the coincidence has it almost seems like there's like an onus on someone who would claim it's a mere coincidence here.
Yeah, exactly. Yep, for sure. Okay. So I don't know how much further you want to take this. Like, I know
I have another 20 minutes.
Okay.
So if there's perhaps it looks like we're about to finish part 1, so that might be a natural stopping point.
Yeah. So basically, the whole purpose of doing is for reinterpreting, to try and interpret Planck's constant. So we could maybe go through this, because this isn't really that long in terms of how to interpret Planck's constant. Okay. So, and this action constant, because action is kind of a difficult thing to understand. Okay. So here we're, the units of Planck's constant interpret differently than the standard language. So it is action per cycle. And of course, if you're calibrated to the radian, it would be action per radian. But I'm just going to stick with the cycle. And then just so, the audience knows that if you want to switch to the radian, then you need to use angular frequency and H bar, right? That's just the way it is. And so what I want to do, so what I did here is, so action's kind of hard to understand. So I'm going to do a little algebra on the units, and I'm going to write the units like this. I didn't change anything. All I did was just, I pulled the J out. And now with this cycle term here, I can read Planck's constant as the energy of one wave period, right? So it looks to me like Planck's constant could be the energy of one wave period. So if you have a wave with a certain wavelength, it's going to have a wave period. In other words, it's going to propagate that distance in that time, right? So you can think of it as a wavelength, or you can think of it as, how far the wave propagates in that wave time, right? And so this is more temporal. This is in temporal description of H. So H is the energy contained, say, within that one wavelength. That's how I'm seeing it.
Okay, can you go back? So you're drawing an analogy between this and something with wavelength. Can you go back to the wavelength thing? Because I wasn't ready for that, and I didn't fully assimilate it.
So each wave has a wavelength. So if you have a wave of a frequency F, each cycle has a wavelength, and each cycle has a wave period, right? And so H is the energy. So these units, when you rearrange them like this, read the energy of one wave period. So it seems like that's how I'm reading this. So this it seems like H is, it's usually referred to as a coupling constant, but it seems like when I do this rearrangement that I can read so instead of being and so the action is one cycle. So it's an action constant, but the action is one cycle. Without this delta term here, it's hard to see that the action we're talking about is on a per cycle basis.
Okay. So I'm a little skeptical because maybe I have a feeling I'm just quibbling with you about the words, but the words are very important because that's how we grasp it.
Yeah.
So I think, but anyway, so it's the energy of one period is what you're saying.
One wave period, yeah.
One wave period. Okay.
Yeah.
Well, if I imagine a wave constrained on a string, a wave constrained on a string, okay? And if I take away friction, let's take away friction because at this level, there isn't friction. The waves just carry on.
Yeah.
This doesn't feel quite right to me because that would imply that more energy is occurring over time. Every time like a hump goes up and down and then back up again, that's a certain amount of energy. Down, up again, and more energy. Down, up again, more energy. That's not what's going on, right? Or it is. Is that what you're saying?
Well,
that each new oscillation carries with it more energy. I would imagine that the fact that
no,
is this oscillation is a certain amount of energy. And if that oscillation is extinguished, then that energy is carried off somewhere else.
Yeah. So I like to think...
So is it really the energy per period?
Yeah. Is always the same.
But that makes it sound like there's more, like every new oscillation carries with it more energy. And that's not what's going on. You're saying that like the fact that this oscillation is there has a certain amount of energy.
Yeah.
So like I like to think 1 joule, 2 joules, 3 joules. It's like, no, this is 1 joule. The fact that this is here is just 1 joule. Okay. So I'm having trouble understanding it because of that language.
Yeah. Okay. So I'm going to show a picture here.
Okay.
This is actually this is what I intuited from my capacitance, my capacitor deriving Planck's constant from the law of capacitance. So I'm kind of like pretending that here's 2 capacitor plates and that there's a certain amount of energy inside those 2 capacitors. So you can think of that as, so each wave period, so each thing inside this box here contains the same energy H. But because it's propagating, right, because it's propagating, more energy units enter the detector in unit time for this one down here. So this is a bigger wavelength, right? It's a bigger size. I just drew it as a bigger size because in my capacitor derivation, there's 3 parameters. There's area, like length, width, and divided by the distance between the capacitors. And they're all the same to me in order for this derivation to work, they're all the same. And so you got the length and the width are the same as the wavelength, right? So that's a longer story. This is just the picture to show how, let's say each dot is the same energy. And so when you have a higher frequency, you've got more energy units entering the detector per unit time, right? So I prefer to think of traveling waves rather than standing waves and I prefer to think about what's happening at the detector, right? So when you have a higher frequency, you have more energy units hitting the detector per unit time, per 1 second, say.
I see.
Right?
Part of what's going on is I prefer to think about standing waves myself.
Yeah, I know, because you play with strings. So
I guess whatever the reason, that's what I tend to think about, but I see it your way.
Light is a traveling wave, and so it's easier to think of what's going on at the detector in terms of like all the things in physics. Actually, we can't see waves when they're traveling. We can only see waves when they hit a detector. So it's easier to think in terms of what's hitting the detector.
I think you're right.
What is getting absorbed by the detector?
Yeah,
It's just
the
easier to
traveling wave is more fundamental than the trapped wave. So
yeah, exactly. And
that's
like
my
then if
reason.
you have trapped waves, then you want to talk about lasers. So I think it's just easier to say, okay, we want to know what the nature of light is, and light is a traveling wave unless you contain it somehow, right?
Don't we want
to know.
Sorry.
Yeah, we want to understand the traveling wave. What is the nature of the traveling wave? So
can't we eliminate any like confusion by changing it from the energy per period to just the energy per cycle? Because the cycle is the actual
are the same. Period and cycle are the same.
I don't think so. Period is an attribute of a cycle. It's the amount of time it takes.
Wavelength is also an attribute of
yes. So we want to say the energy per cycle, not the energy per attribute of that cycle.
Yeah. And so that's where I'm getting.
I think that's why I'm getting messed up. But you would still be okay, but you still agree with energy per cycle.
Yeah,
if I want to say it that way, you're not going to debate with me. Yeah.
It's the energy of one wave period. It's the energy per cycle. Like this can work out many different ways. And so this is where, I'm going to kind of take it to the next level here.
Cool. Okay. I'm on board. It's the energy of one cycle.
It will be per cycle once I do this next step here.
Okay.
Which is where this is the work of Juliana Mortensen, or her married name is Juliana Brooks. And so she wrote a paper where she claimed that Planck had used to have a time variable in the energy equation. So she claims that there's a hidden time variable in the energy equation, and that should be written E equals H times frequency times this hidden time variable. Okay, so I went down. So I actually agree with her. It makes sense to me. Okay, so basically what I'm doing is I'm refactoring the units based on this this assumption that there's a hidden time variable that through some mathematical manipulation called Wien's law, it was actually factored out. The time variable was factored out. It was set equal to 1 by accident, and then it disappeared. They didn't have to write it. And so the claim, the idea is that there's a hidden time variable in the equation. I'm not adding a time variable. The time variable should have been there, and that the S from the action constant belongs to that time variable, right? And now H becomes, so now H has the units of joule per cycle. So if I'm allowed to do this, and I don't think there's anything wrong with doing this, at least as an experiment, as a thought experiment to see, does this make sense? Okay, so, and the reason for this is, so why does this make sense? Because Planck's energy equation was derived from the black body experiments. I think I spelled experiments wrong. Makes sense to write this equation in terms of an experiment. So experiments are temporal. So an experiment usually is temporal. Usually it takes time to do an experiment. And so putting the time variable in here turns this into the equation of an experiment. And so now H has units joule per cycle. The time has units second. And of course, frequency has units cycles per second. Everything, works out nicely, and we end up with the units of joule like we wanted to. Okay. And so another motivation for this had to do with MRI physics. So, I work in the field of medical imaging, and, I'm surrounded by MRI physicists. And so I sat in on one of their classes, and the very first slide they put up was written like this. And so it's not E equals HF, it's delta E. So we're talking about changes in energy here, right? When a detector absorbs energy, there's a change in energy. When an electron absorbs energy and jumps up a level, there's a change in energy. So change, of course, takes time. It's a temporal thing. Change and time are the same thing. Time is an emergent property of change. If things weren't changing, there'd be no time, right? So that's sort of the motivation. So this delta term here kind of gives me permission a little bit to put that time variable into the equation. Okay, and then when we set the time variable equal to 1, you know, we end up with, we're back to where we were before.
Okay.
So I think that, so Juliana Mortensen, I agree with her. So I say, I believe that through the, you know, manipulation of whatever Planck did when he was trying to derive his equation, and it had to do with using the speed of light. So when you use the speed of light, you write in the number 300 million meters per second, you are calibrating your equation to the 1 second time period. So as soon as you plug the speed of light into an equation, you are hard coding 1 second into that formula, because you write the number 300 million, and so that's how many meters are in per second. So you're kind of hard coding to the 1 second. A lot of our formulas, a lot of our equations are calibrated to 1 second, and we don't know it because we don't write it. We don't, you know what I mean?
Yeah.
We are literally, like when we switched from the CGS system to the MKS system, the only thing that didn't change was the 1 second. We've always been calibrated to the second. We just, you know, forgotten, I guess. So in this equation, I feel like the time variable should have been in here, right? So if you're running a 10-second experiment, say here, if you're running a 10-second experiment, then the energy you collect in 10 seconds is going to be HF times 10, right? And then if you want to get it in terms of 1 second, you divide by the 10 seconds, and then you get it in terms of 1 second. So you know what I mean? Like this.
I'm still having trouble with this, but I'm getting closer. So here's my first attempt. Here's one of the things I'm doing to try and understand this. So before, I was giving you a hard time about the idea of energy per period. I was like, isn't it energy per cycle? But it is energy, but it's also...
You have to say the word energy of one period, not per. Per is division, of is multiplication, right? So the energy of one period is the same as the energy per cycle, because right? So you're either multiplying or dividing. So you can't say energy per period. You have to say energy of one period or energy per cycle. So,
I know you sent me an email on this. I still don't understand energy of one period. I'm not sure what you're saying there, but energy per cycle makes perfect sense to me.
They're the same. It's two ways of saying the same thing.
Okay, I don't see how, but I can just focus on the part that does make sense to me.
Okay.
So for now, I'm sure the rest will come soon. So
and so this gives me permission to say that.
So what I'm seeing here is I imagine I'm at the beach and I'm letting the waves hit me one by one, and if I multiply the energy per cycle of the waves by the number of seconds I stand there at the beach, then we get the total energy I absorb
in that time frame.
In that time, over the course of that time frame.
Exactly. And so that's easy to visualize. That's exactly what that picture I showed you earlier. Where is it? That's what this is showing, right?
Okay,
so in the 1 unit, in 1 second, all of these waves are going to get absorbed into the detector, but less waves are going to get absorbed into the detector, and less wave. Now I make them bigger. I don't know if that's the right thing to do. I think it is actually the right thing to do. I'm showing the amplitude as being bigger, but this is really just a schematic, because the amplitude doesn't have to be bigger, but I think it is. And that's based on what the email that Chantel sent recently about the energy being proportional to frequency instead of frequency squared. And that, you know, she talked about the oscillator. If you have like spring mass oscillator and you change the frequency very slowly, the amplitude will change such that the coupling constant remains constant, or the, you know, the action constant remains constant. I think that's what's going on here. So again, that's maybe another longer story to talk about whether that's true or not, because there has to be a reason why H is constant, right? There has to be a reason why H is a constant. And so if in my picture I had the amplitude getting bigger, but H is still the same within that bigger space, what Chantel said in that email kind of gives me permission to do that. Whereas I didn't have a good reason to do that before. Before I just did it because that's what my capacitor analogy wanted me to do. But now I kind of have a reason for doing that. And that means H is going to be, H is the same. It's a constant. It's the action of one cycle. And that whatever that action is conserved. And so what Chantel sent in that email was that action is conserved. And, that is technically correct. And that's why H is constant, right? So it gives me a reason to, in my mind, a reason why H would be constant and not, because there is no amplitude, right? There's no amplitude term in this equation.
Yeah.
But there's no amplitude. And the reason you don't need amplitude is because of this adiabatic, I don't know if I'm saying it right.
Adiabatic.
That action is, so the wave conspires to have an amplitude such that H is constant. Right.
Okay. So I'm still putting a lot of that together. What I have for now is that I continue to see this as a very promising line of inquiry because it seems to be telling us that like I'm already certain that there's an ether. And now this seems to be telling us something about the ether. It seems to be telling us that the medium waves in such a way that there's a certain energy, a certain amount of energy per wave cycle. And you've said some things just now regarding, well, how is that possible when normally the energy is actually proportional to the frequency squared? And well, here's the thing. And you've said some ways that might end up being the case. Whatever that is, that's telling us something about the nature of the ether, telling us something about the inner mechanics of the medium. And so that's why I find this line of research very tantalizing. So thank you very much for showing me.
Oh, you're welcome. Good.
Yeah.